Hey guys, welcome to the next video. So in the previous videos, we talked about electrophilic aromatic substitution. We went over all the different types of reactions, how we can add these functional groups to benzene. So now we're going to talk about something a little bit different. Obviously, we're going to be still using what we just learned, right? And to start off, we're going to examine this structure. All right. Now, I picked this one arbitrarily. What I want to do is I just want to talk about these some terminology you guys are going to hear when we talk about benzene and when we have substituents on benzene. All right, we're going to hear the terms ortho, meta, and para. So what does this mean? So ortho, right, and when I'm talking about, let's say, this substituent on benzene, right, I'm going to talk, it's on this carbon. So if I'm going to say that something is ortho to that OCH3, that means it's going to be on that carbon or that carbon, one away. Meta is going to be 2 carbons away. All right, and para is directly across. All right, ortho, meta, and para. So commit that to your to memory because you're going to be using it a lot when we're going to be talking about what's going to be in this video, right? And so we're going to now look and see what's going to happen if we use this compound in one of our, let's say, when we want to do one of those electrophilic aromatic substitution reactions. All right, so we have this OCH3 on it, so we're going to need to examine the effect that this OCH3 has. All right, and what we're going to do is we're just going to examine it by doing the nitration reaction. All right, so if you guys remember the electrophile in a nitration reaction is this compound, NO2 plus. All right, so we're going to attack this guy and we're going to do it from different positions in this ring. All right, so let's see what happens when I attack it right over here using this double bond. Attacks this nitrogen, brings that double bond up, and we're going to get this structure. All right, here's our OCH3. So far nothing is different. Here's our H that we had here, right? So that's still there, and now our NO2 is what we added. All right, and we just lost that double bond, and we're going to put a carbocation on this carbon, right? That was also part of the double bond. So we have a carbocation there. All right, and now remember we had this uranium ion intermediate where we can resonate this around, giving us this intermediate. So I can move the double bond up here. Carbocation moves down there, and we have the double bond there. All right. What else can I do? I can move this over there and create this intermediate, OCH3, carbocation here, H, and then NO2. All right. What I want to do is I want to look at this one, actually. So what I'm going to do, remember this oxygen has lone pairs. I can resonate one of these down as well and create this intermediate. Put that positive charge on the oxygen. He still has one lone pair. Here's our H, and here's our NO2. All right. This is the key intermediate. When we do this reaction with OCH3 in this position, right, where the NO2 is on the, let's use our new terminology, the ortho position, it's one away from OCH3, we see that that positive charge, the carbocation, is resonance stabilized, which is great. So we're going to keep this in our heads for now, and we're going to see what happens when we attack from another position. All right, so let's redo this, and now I'm going to put this over here. And now what we're going to do is we're going to attack from another carbon. So here's our intermediate. And we're going to attack using this double bond instead now. All right. So what's going to happen is, here's our OCH3. All right, I'm putting the nitrogen one carbon away now. That NO2, NO2H. That double bond, nothing happened to it, and the positive charge is now over there. All right. And so now the NO2 is on the meta position. So let's look at our uranium intermediate. So this is the reason I was constantly showing this when I was going through all the electrophilic aromatic substitution reactions. All right, so we have this guy. Positive charge now over there. I can move him over there, creating this intermediate. Oh, sorry about that. Positive charge here, HNO2. And over here, when we attach the NO2 to the ortho position, we were able to resonance stabilize that carbocation, right? We had that at one point we put the carbocation directly underneath that electron donating group, and we could have resonated down a lone pair. In this case, we can't do that. There's no way you can get the positive charge directly at that carbon of the OCH3. So in this case, this carbocation is not resonance stabilized, and so this is when we put the nitro group on the meta position. All right. So now we have one more position to try, the para, and remember that in this case, the ortho position here and here are the same, so we don't need it. It's not like we need to try it twice, and same thing for the meta position. So now let's try ortho. Sorry, para. Here's our OCH3. All right, here's the electrophile. And so now let's attack and put it on the ortho position. Sorry, the para. I don't know why I keep saying that. All right, here's the NO2. And now our carbocation is going to be there. And so now let's look at our uranium ion. Move that double bond over and create this resonance structure. That was a bad drawing. And now the carbocation is over here. And now, remember, we have two lone pairs here. And now we're in a position that we can resonate this down. And stabilize that positive charge. So we created, again, a similar intermediate to here, but the nitro group is on a different position. So you see that when we did the ortho and para positions, we were able to stabilize our nitro group, our carbocation. This is going to be the important thing. When we have electron donating groups on our benzene, they are going to be called ortho-para directors. What this means is that they will they will prefer for the whatever we're adding to be either on the ortho position or the para. We can get a mixture here. All right. So that's the thing you need to watch out for. Meta is not going to be the major product because we cannot stabilize this carbocation. All right. So we have ortho-para directors. Now, the one thing that a lot of people mix up is the thing that does the directing is on the ring. So the director is this OCH3. A lot of the times when people see, you'll learn how nitro groups, when we have an NO2 instead, they're going to be meta directors. They get confused thinking we're talking about what we're adding. the director is what's on the ring already. That tells you where what you're adding will go onto the ring. So in this case, when we have OCH3, we're going to prefer to go to the ortho position and the para position, not the meta. All right. Now, again, there are other things like sterics that can come into play to tell you where the if it's going to be more para or more ortho, right? But that's going to be for a later discussion. Usually, the general idea is that if you have a large group, that the major product is para. If you have a less sterically hindered group, it's going to be ortho. All right. So let's go on to the next example. So I'm going to erase this here. So we just saw the effect of an electron donating group. Now let's go on to an electron withdrawing group. All right. So what we're going to do is we're going to, again, draw the benzene. All right. And now what we're going to have to do is we're going to show, since we just saw the effect of a donating group, we want to examine the same exact effects that happen with a withdrawing group. So let's do a nitro group. All right. So now we have this nitro group. So erase this and make it a little better. All right. And so what we're going to do is we're going to just do the same thing with the nitration. So here we go. This here, and now let's again go through everything, ortho, meta, and para. So let's start with ortho like we did before. Attack the nitrogen, bring this guy up. And now what we're going to have is we're going to have NO2 over here, the original one, our H and the NO2 there, and the carbocation goes there. All right. Remember, we can have the uranium ion intermediate where we can resonate them around. Now, in this case, the other resonance structures aren't as important to get across. What is important is right here. We have that carbocation at the carbon with the NO2. Now, nitro groups are electron withdrawing groups. All right. So these groups are not great when we have a positive charge next to it, right? Because remember, positive charge, when we have carbocations, they're electron deficient groups, right? They don't have as much electrons. If we put it next to an electron withdrawing group, think about it as getting a little bit even more deprived of electrons, right? So that's not going to stabilize it. It's actually going to destabilize it. So when we had this compound, this donating group, having the positive charge there, right, was actually good. In this case, it's actually bad. All right. So that's the takeaway for what happens when we add it to the ortho position. Now let's see what happens when we go the meta. All right, so now what we're going to do is we're going to attack meta. So we're using this double bond. So remember the meta is like the 2 positions away, right? And now what we're going to do is, remember that double bond stays, and the carbocation that results is right there. Okay, and now let's try to resonate this guy around. Sorry. Carbocation moves there. NO2 here, NO2 and H. All right, now let's resonate him again one more time over there. And we get this intermediate, or this resonance structure. with the carbocation right there. So these are the possible resonance structures. Now you see that in this case, we completely avoided having a carbocation on that electron withdrawing group, or closer to that, on that carbon with the electron withdrawing group. This is good, right? If we had it at the carbon of the withdrawing group, like we did at the top, when we did the ortho position, it would destabilize the carbocation. That's not favorable. In this case, we completely avoided that. So this is favorable. So in this case, the meta is more favorable. Now let's look at para. So we're going to get what looks like this sort of structure. HNO2, carbocation there, original NO2. All right, and now let's resonate. Move that over. We get what looks like this. Carbocation on that carbon. H, NO2. So you see we put that carbocation on the carbon with that withdrawing group. Not favorable. Remember, not good to have withdrawing groups next to electron deficient carbons or atoms. All right, so this is the same case as what happens with the ortho group when we directed at ortho. So the takeaway here is that when you have a withdrawing group, they direct meta. All right, your new group is going to be directed to the meta position. All right, and when you have electron donating groups, it directs para or ortho. All right, and so that's going to be the main takeaway for here. So let's write that down. So we're going to have electron donating groups equals ortho / para. Electron withdrawing groups can be meta directors. All right. One thing that we should watch out for, though, are halogens. So let's erase all this. Actually, even before we even mention the halogens, let's mention one thing. I wrote up here activating and deactivating groups. What does this mean? We have a benzene. When we talk about this, we're going to compare everything to just a plain old benzene. And I compare, let's say, this guy, OCH3. Which one is more reactive, right? This guy, because he can stabilize those carbocations, right? Let's say if we do like that nitration, if we wanted to add that do the nitration to it, and that's like our intermediate, he is going to react much faster than benzene will, because he can stabilize that carbocation, that intermediate, whereas benzene doesn't have anything to do that. So this OCH3, we call it an activating group. All right, this is an activating group. When we had this situation, this nitro group, this is going to be considered a deactivating group. Now, why is that? Remember, we did not want to get the carbocation on any of the carbons with the nitro group, right? So essentially, we had to kind of dance around that carbon, so that couldn't stabilize it. And if in the other, when we directed Ortho-para, you did get the carbocation at that nitro group, well, then you even destabilize your intermediate. So it's going to react slower than benzene, because this group is called a deactivating group. Think of it, it deactivates your benzene. It makes it slower. All right, so that's what it means. So let's add on to what we have here. Activating equals faster than benzene. Let me move this up. Deactivating is slower than benzene. All right, so you guys can see that resonance plays a massive role in all of this. Okay, and what they'll give you on the test is they're going to give you this chart. All right, or at least I hope they will. So this was given on the 2019 exam 1, and so it tells you all the ortho-para directors and the level that they activate. Okay, so you guys can see. Let's look at this chart. We're going to go through everything one by one. So let's first look at the ortho-para directors. So remember, we have a benzene like this, and we have, let's pick a strongly activating group, NH2. Right, this guy is going to react very well. So what he's going to do is he's going to direct ortho or para. So we're going to have NH2, NO2, or NH2, NO2, right there. So that's an ortho-para director. We can examine the resonance, but it's going to be similar to the OCH3 example, right? And he's strongly activating. What this means is that if we compare it to regular benzene, he is going to be a much faster reactant in an electrophilic aromatic substitution reaction than benzene will. All right. The whole reason is because it puts more electrons into that into our pi system. It can pump in electrons from the lone pairs on the nitrogen. Then we have these moderately activating, so we have these amine groups. We have OCH3 and OR. OR is just any alkyl group. And remember, and you can see OH and O minus are more activating than OCH3 and OR minus, but they're still ortho-para directors. Let's not forget that. Now we have alkyl groups. These are weakly activating. So if I put, let's say, a methyl here, methyls are weakly activating. They don't resonate, but remember, through hyperconjugation, they're still electron donating groups. So you can think of it as a fake resonance, all right? If that helps you in your head. And now you can see when we get to the bottom, halogens, all right? These are ortho-para directors, yet they're weakly deactivating, all right? Now, this is why I wanted to talk about the halogens before, all right? So let's erase this. So the halogens are kind of the exception. Usually when you have a donating group, you are you're an activator. All right. So if I put, let's say here, chlorine. All right. Now chlorine or the other halogens, these are deactivating groups. Now why is that? Because remember, they're very electronegative. So they kind of they would pull the electrons towards themselves, right? Remember, they have this induction effect, all right? Yet so that's why they deactivate. So they're going to be, if we compare it to benzene, this benzene by itself reacts faster than if it had this chlorine, because the chlorine deactivates it. So that's the case of how it's a deactivating group, but then why does it direct ortho and para? So if we examine this, if we did the ortho, so let's see, nitrogen, and let me erase this arrow just to eliminate confusion. We're going to get this. Chlorine, and we have the carbocation on that carbon. All right. So again, we can resonate it all around the ring, but what I want to do is examine this specific resonance structure. This chlorine has 3 lone pairs, and it can resonate down and stabilize that carbocation. So this actually, remember, resonance still stabilizes our intermediate, and this is the reason it's going to direct ortho. And if we did the para version, we'd get this intermediate. I'll just skip ahead to what the intermediate itself would look like. All right, we're going to put carbocation right there, double bonds there, NO2. And so when we resonate 1 pairs down, we get this. All right, and so this is the para-stabilized intermediate. In meta, we're not able to get it on the carbon with the chlorine. So while halogens deactivate, when we actually do the reaction, they can still stabilize through resonance. All right, so this is why they still direct ortho-para, but they deactivate, which means they react slower than benzene. All right, so that's something that you guys need to watch out for. It's a little bit of the exception to the rules. All right, so definitely watch out for that. Now, if you look at the meta directors, right, most of these are all withdrawing groups, electron withdrawing groups. And so we have these strongly deactivating groups like NO2, that nitro group, CF3, right? If we drew that on a benzene, that would look like this. Right? Remember, the fluorines are very inductive because they're electronegative, and so they'll pull electron density this way out of the ring and deactivate. All right, and these are all meta directors, right there. So it's a useful chart. The more you practice, the better at this you'll get. And over here, just in case you guys weren't sure, CHO, all that is, I'm going to just erase this over here. That's just an aldehyde group. So something like that. Or CO2H carboxylic acid. So I just put this over there. Oh, CO2R, again, is just going to be an R group. So get used to that kind of nomenclature. And that C triple bond N, right? You guys saw this one already. That's just going to be this. So those are all withdrawing groups. Right? And sometimes you'll just see it written as CN this way. All right, and so those are activating and deactivating groups. In the next video, we're going to get into some other minor things about the effects of some of these groups, and we'll do a couple examples. All right, see you guys in the next video.